Estimate the area under the graph of f of x equals 25 minus x squared from x equals 0 to x equals 5 using 5 approximating rectangles and right endpoints. So what this means is we're supposed to figure out the area between x equals 0 and x equals 5 under this curve. So we're looking at this area here that I'm highlighting in yellow. Now, in order to figure out this area, we're supposed to divide it into 5 approximating rectangles, which means from 0 to 5, we split it into 5 different parts. So that will give us our intervals for our rectangles. Now let's clear this up and see if we can draw in our rectangles. So in order to draw our rectangles, we first split our interval. So we're using 5 approximating rectangles, so we need 5 spaces. So 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5. Those are going to be the bases of our 5 rectangles. Notice they are all the same width. They're all a width of 1. Now we need to draw from these rectangle bases that we have marked all the way up to the graph. So let's see if we can draw this up. So that one looks like it's right here. We're going to go all the way down. There we go. And then the next one looks like it is right here. I'll go all the way down again. And the next one looks like it is right here. And then right here. And this one looks like it meets at 0. Now it's saying to use right endpoints. So that means we go to the right side of each of these intervals to draw our rectangle. So here's our first rectangle. Here's our second, our third, our fourth, and our last. So now we have our rectangles, and notice that the right top corner of each rectangle is what is hitting the graph. So that means that we are using our right endpoints. So now we need to figure out the area of each piece. When we try to figure out the area of each piece, we're looking at the base times the height. For this one, we can read it off from the graph, but there's a second way that we can do it. I'm going to show you that at the same time. The second way that we can do this is we can say that the area is the base, which is 1, times the height. And the height is the right endpoint. So for this first endpoint, it would be at x equals 1, put into our equation right here. So that'll look like 25 minus 1 squared. Now, if you notice, 1 times 25 minus 1 squared is 25 minus 1, which is 24. And notice we put our dot right here at 24. Let's try the next one, plus 1 times. So now we're looking at our second interval from 1 to 2. It still has a base of 1, but now it has a height of 25 minus 2 squared, which will look like 1 times 25 minus 4 is 21. And we can see that's where we put our dot. If we keep going, we have 1 times 25 minus 3 squared. And then we have 1 times 25 minus 4 squared. And then we have 1 times 25 minus 5 squared. And that takes us all the way across. 3 squared, that's this interval all the way up right here, is a distance of 1 across. The base is 1, and the height, and then the base is 1, and the height, base is 1, and the height. So if we move these through, we'll have 1 times 25 minus 9 gives us 16. Plus 1 times 25 minus 16 gives us 9. And then 1 times 25 minus 25 gives us 0. So while we can read it off the graph, sometimes it's hard to see on the graph. Sometimes you don't have a graph. Sometimes you didn't create a graph. This graph goes up to 25. What if it was 100 minus x squared? That would be a much larger graph. It might be harder to read to have accuracy. So another thing we can do is put the x values into the equation and solve down to figure out our height for our different rectangles. Now remember, we're using the right side of the intervals here. So when we switch over to the left side, we'll be careful. We'll make sure we have it. But we're using the right side of our intervals here, which is why we used our values from the right sides. If we simplify this down and add this all together, we'll get 70. And there is a lot of gapping space between our rectangles and our curve. So I'm going to say this is an underestimate. Now in part B, it is asking us to repeat the process, but this time to use left endpoints. So I'm going to leave my lines drawn where they are, but now we're using the left side. So I'll put this in blue. So the left side of our first interval is at 0. Then we have the left side, left side, left side, and left side. There we go. So now in order to have our rectangles, we're not going to use the dots on the right anymore. Now we're using the dots on the left. So if we put this all through, let's do our calculations. We have 1 times 25. What is the left endpoint of our first interval? It looks like it is 0 squared plus 1 times the left endpoint of our second interval looks like it's right here at x equals 1. The left endpoint of our third interval, it looks like it is right here at x equals 2. And then the left endpoint of our fourth interval is right here at x equaling 3. And our last left endpoint is right here at x equaling 4. So if we solve this down, we'll have 1 times 25 plus 1 times 24 plus 1 times 21 plus 1 times 16 plus 1 times 9. And if we solve that all down, we'll have 95. And these are extending above our graph. See all this extra space above the graph? So we're going to call this an overestimate. So for the first part, we had an underestimate. For the second part, we have an overestimate. What this does is it bounds our region for our actual area. So we know it's not going to be lower than 70, and we know it's not going to be higher than 90. So it gives us a nice bounding. It has the over, it has the under, and that's okay. We're just looking at an estimate. For part A in purple, we used our right endpoints, and for part B in blue, we used our left endpoints, and we were able to calculate our estimates for our area under the curve.